Welcome, Regents students, to the start of what is obviously a very unusual school year. It's going to be challenging. There's going to be a lot of things we're going to have to overcome, obviously, but hopefully we'll have some triumphs as well. I'm going to do my best to give you a good educational experience, and I hope that you do your best to make the best of the situation that we have here. Now, you probably have a lot of questions on your mind, things about grading, the procedures of the class, Google Classroom, but hopefully among those many questions is, what is physics? What is this thing that we're going to be studying all year? And, I think we've had so much information about the technology and all that. I prefer at the start of the year to answer that question of what is physics. And that's what we're going to jump to today. The rest of the stuff we'll figure out as we go along. I'll give you more information in the Google Classroom stream, but right now I just want to focus on the question of what is physics and where do we begin the study of the topic. So what is physics? So physics is concerned with all places, all things, and all time. And physicists are trying to discover the principles behind why everything happens at all times. So imagine very large things, like when you look out at the night sky and you see the twinkling stars. You look at this tiny little speck in the sky, and now we know that that tiny speck you might think is a tiny star, but actually it could be an entire galaxy. We're in the Milky Way galaxy. There are billions of stars in the Milky Way galaxy, our sun being just one of them. So when you're looking at that tiny little speck, perhaps it's possible that that is an entire galaxy of billions of stars. Maybe there's planet Earths over there, or maybe not. Maybe everything is all different volcanic planets, all on that tiny little speck. Physicists are interested in that giant thing that's small by that enormous distance in between. So physicists want to know what's happening in that world, all the way on the opposite side of the universe, okay? So huge things, okay? But physics is also small. So forget about the galaxy very far away. Go smaller and smaller, maybe into your own finger. And inside your own finger, we know there are cells. Within the cells, there are atoms and molecules and atoms. And inside the atoms, there's even protons, electrons, and neutrons. And you may not know this, but the protons and neutrons, there are things inside of those even. So imagine something so small you can't even imagine. Atoms are small. Now protons, and inside protons, that tiny, tiny thing, almost as unimaginable as the giant thing out there, the galaxy, that physicists are also interested. So you see the scale, huge things beyond our imagination and small things beyond our imagination. Physics is looking to understand all of that. And time, all of time. So you may have heard the expression, the Big Bang Theory. Well, there's a popular show out, the Big Bang Theory. You may have watched it. But the Big Bang Theory is that everything, that galaxy that you see in the night sky, us on planet Earth, that little tiny molecule in our finger, all that stuff was at one point crushed into one tiny point, smaller than the head of a pin. Our sun, Earth, the whole universe, every black hole, everything was inside one little speck and exploded in a tremendous explosion 13 billion years ago, with a B, not million, 13 billion years ago. Physicists want to go back in time, well, not physically, but in their imagination, and understand that moment, that Big Bang. And then everything from that moment to our present moment, how things sort of evolved, how we got atoms, how we got planet Earth, how we got the sun, the galaxies, How did all that stuff come about? So all of that time to this moment. And then from this moment all the way to a possible end of time, maybe 13 billion years in the future, do we collapse back in and everything destroys itself in a point? Or do we expand forever? Huge questions of time also. That's physics. We want to know why things happen, why they happened, what might happen, and all the processes and all the laws that govern all that. Enormous task. So the first thing we're going to begin today with is the most basic thing of why that happens. We can ask that in terms of why things happen to us on a daily basis. Like, for example, I'm here talking to you on the camera. You're at home probably. How did you get there? How did I get here? How do I go to the grocery store? Because our little world, compared to that giant one I described, is part of that big world. So if we just think about what's happening with us, we can get an understanding of the universe. And the obvious thing of how something moves is by you possibly, or a machine, pushing or pulling on something, which is what we're beginning with. The concept of force, as we're trying to understand the black holes and all the tiny things, we realize that things change because of forces. So that's the place where we begin today. So what is a force? The first thing is, it's any push or pull. So pushing, pulling, those are forces. Okay? What do forces do? Well, obviously, they can make something move. Like, maybe you want to rearrange your bedroom. And so, let me just see if that's on the screen. Yeah, okay. So, you want to rearrange your bedroom. So, what you do is you take your bureau and you push it, right? And that's going to cause it to move. So, pushes can make things move, but so can pulls. Like maybe your bureau's up against the wall, so you can't get behind it. So, you could pull it and make it move. Make something move. But they can also, I'm going to keep it under this same bullet. They can prevent something from moving. Okay? Think about this. Maybe you're babysitting someone, a kid, and you see the kid, the ball starts rolling out into the road, and the kid starts running without looking. So what you do is you grab onto the kid and you pull on that kid, right? And the kid's trying to go, but your pull isn't making the kid move. It's making the kid stay at rest. So pushes or pulls can prevent something from moving, or they can make something move. Okay? Now, I just gave you an example where you are supplying forces. You're a living thing. You have muscles and skeletons and all this stuff, so and nerves, so we understand that from biology. But other living things obviously can create forces. Horses can pull a carriage, things like that. But it turns out that not only living things create force, non-living things create force too. So, caused by living or non-living. So let's see. Well, I've got this marker, right? So I let it go and it falls. So in order to prevent it from falling, I got to get my hand under there and I've got to hold it up. Okay? My muscles are in my body are holding that up. So muscles, people have those to create force, right? Well, think about this. I put this now down on a table. Table has no muscles, has no bones, no joints, no tendons. It creates force and it has no moving parts whatsoever. So any living thing, every living thing in the entire universe creates force all the time. We're going to learn later in the year, it never stops. That table is creating a force even when there's nothing on it. Okay? It's creating forces, multiple forces. Okay? So these are some basic things about force. But another thing that's common sense is you can push very hard or very lightly. So forces have a strength to them. Okay? The fancy word, well, they have like a size, is the fancy word for that is magnitude. So forces have magnitude, and that's a fancy word for a size. Well, I'll talk about, the numbers associated with force in a minute when I get to the next thing, Newton. But they have size, magnitude, and direction. So think about this. I gave you that example of babysitting, holding the kid back so that they don't run into the road. So you're pulling them away from the road. What if you're on this side and you pull them toward the road? Right? You're going to propel them right into the road. Wow, that's a big difference in outcome. So forces have direction. It makes a difference. A fancy word for things that have magnitude and direction are called vectors. So that's a V, vector, okay? We'll be using that term more often. A thing that does not have direction is called a scalar, like the temperature of the room. If, for example, it's 70 degrees in here and I turn around, it's still 70 degrees in here, right? So temperature doesn't have direction, so we call it a scalar. And the last thing, what are forces measured in? In everyday life, when you go to the gym, for instance, it's pounds. So you lift a certain poundage, a certain force. But that's the American unit of force. In physics class, in science classes, the unit of force is the Newton. Okay? So I'll give you an example of a Newton in a minute. Now I just realized that I forgot a spring scale, so let me pause the video and I'll come back with a spring scale to give you an idea of what a Newton is. Okay, so I'm back. So this is a spring scale. It just basically measures force in newtons with a spring inside, so spring scale. And basically you could see that newtons aren't all that big. With my pinky, I can easily put 20 newtons and beyond. So a newton is smaller than a pound. In fact, I think it's about 4.5 newtons is equal to 1 pound. But so you get an idea. I pull a little bit, it's a small amount of newtons. I pull more newtons. Makes sense, okay? Now, what we're going to do today is we're going to learn how to represent forces on a piece of paper, okay? So it's very logical, very much common sense. So let's take a look at a couple examples. So if I had a force to the east, well, what has a direction in drawing? Arrows. So that's what we use to represent forces. So let's suppose I draw an arrow like this. And I know that that is 10 newtons east. Okay. What if I wanted to draw 20 newtons to the south? Well, obviously I go down, if like I'm looking on a map, I'd go down this way for south. And to make 20 newtons, I'd probably draw, you'd probably say, well, maybe you should draw a longer arrow. And you'd be correct. So what we would do is draw an arrow twice as long to represent 20 newtons, and we just draw it into the direction that it's pointed in. So this is 20 newtons south. Okay, very logical. What if the force is very large? Maybe it's a horse pulling on something and it's like 3,200 newtons. Well, if I wanted to draw this is 100 centimeters. So that's not even going to fit on a piece of paper. So what you can do when forces are very large or too small, what if it was like a millionth of a newton? Well, a millionth of a meter is like you wouldn't even see it. It'd be like a little dot. So what you could do if forces are very large or very small is you could use a scale to convert the forces into a manageable length before you draw them. So let's take a look at such an example. Okay. So F for force equals 3,200 newtons east. And then what we do is we use a scale. Now the scale, sometimes you have to think of it, but a lot of times it's given to you on the Regents. So let's suppose the scale was 1 centimeter equals 1,000 newtons. So how would we draw such a force using a scale like that? The first thing we have to do is we have to use a ratio to convert our length down to centimeters. So what I'm going to do, like when I set up ratios, is I create a fraction on one side. 1 centimeter divided by 1,000 newtons. There's a ratio, a division. And now I'm going to set that equal to another ratio on the other side. Okay, and now I don't know how many centimeters this is, so I'm going to leave that a variable. I'll call it F. You could put X there. A lot of people like X. So you could put X here instead. Fine. Okay. And my force is 3,200 newtons. Now notice I've got centimeters on top, newtons on bottom. So I do the same thing on this side. Centimeters on top, newtons on bottom. And I solve for F. F times 1,000 gives me 1,000 F equals 1 times 3,200. Divide both sides by 1,000, and I get F equals 3.2 centimeters. Okay. So now I can just draw that arrow, 3.2 centimeters long. So I get a ruler. Maybe I'll go down like this. Okay. Now this ruler, like a lot of rulers or meter sticks, you can see it's all banged up on the, and so if we try and use this, because of the wood that's chipped off, we're not going to get a good measurement. The other one I have is newer, but I wanted to use this old one to show you a little trick that you could use. Many of you might already know this trick, but instead of drawing from 0 to 3.2, I'm going to start at 1, the 1 centimeter mark, and draw to 4.2. So instead of from 0 to 3.2, I do from 1 to 4.2, and I've created a 3.2 centimeter long line. Some of you may notice, well, aren't you drawing it 32 centimeters? I am, because if I'm making it bigger so you could see it on your screen. So there's a line, okay? But here's the thing I want to warn you about. A lot of students make this mistake. They say, okay, we need an arrowhead because it's a vector. It has a direction. They draw this nice and precisely. And then they go like this. and you're going to lose points because on the Regents or on a physics test, when your lines are measured to see how accurate you are, your arrows, it's measured from here to the arrowhead. And so that's now wrong. So you don't want to be sloppy with your arrowheads. You want to be very precise. Put your pen or pencil right on the edge of the line as precisely as you can and pull back. Oh, pull back. And then do it again. And there, I have a nice arrowhead, okay, that hopefully is accurate. And you get graded for accuracy on such a diagram. Now, I also want to point out that there are some things here that may not look like a big deal, but on the Regents are a big deal. Units, for example. If I left this off, mathematically I get the same answer. And there's nothing wrong numerically or with our scale, but the Regents takes points off for that. So in the first line of your calculation, you want to have units on everything. Centimeters, newtons. This doesn't need units because it's a variable. So, but newtons here, okay? And I probably should have labeled this F equals 3,200 newtons. Now you don't need units in your algebra, but you need units in your answer. So that's where units in the first step, units at the end, okay? So that's forces, okay? Just a real basic beginning to what is physics. It's the evolution of the universe for all time and all space. And that evolution happens as the result of forces, pushes or pulls, okay, that can make something move or prevent it from moving. They can come from living things or non-living things, things with no moving parts like rocks or tables. Okay, everything in the universe creates force, okay? And then the way we represent force is with an arrow. The longer the arrow, the bigger the force. The direction of the arrow, the direction of the force. Very logical, okay? So that's our first day of physics. I hope you enjoyed. So what you're going to do now is you're going to complete the homework. In the Google Stream, you'll see a unit plan with today's information, today's notes. Open that PDF document. You could print it out if you'd like. And then answer all the questions. And then there will also be a Google Sheet with your name and everyone's name and the assignment. And if you have any trouble on any of the questions, by the way, the answers will be also there in a PowerPoint in the Google Stream. And if you couldn't get any answer, or maybe you got an answer, you still weren't sure how you got it, on the Google Sheet, put next to your name what question you had trouble with. And then I'll know to address that the following day tomorrow, okay? So, and if you don't have any questions, next to your name, maybe just put an X in the Google Sheet. Everyone in that Google Sheet, like a spreadsheet, should be putting in an entry, either an X if you have no questions and the homework went well, or a number, like maybe you couldn't do number 2, so you'd put 2. Maybe you couldn't do 5, so you'd be 2, 5, or this way for you, 2, 5, and I would know those are the 2 questions. Okay, well, thank you for coming to physics class. And I hope to see you tomorrow. See you tomorrow in quotes, right? And okay, till next time. Hello, Regents students. I just wanted to add a little bit of information that I forgot to mention at the end of our lesson for today on force. And that's how you're going to submit your homework. There'll be 2 assignments for today. One is to the notes. So what I want you to do is copy down all your notes in a notebook and then submit photos of your notes, and you'll get credit for that, for taking notes for today. The second assignment for today will be the actual homework. When you're done with that, take a picture with your phone, your computer, whatever, and submit that in Google Classroom, and then you'll get credit for that as well. So 2 things to submit for today. Okay, see you tomorrow.